Hello there, we're going to look at something called differentiation today, and we're going to do differentiation from first principles, and we're going to try to use the gradient that we've already seen at GCSE to try to justify this. Now, do you remember we were doing last lesson, we were doing derivative functions and derivative graphs, and it's all linked together. The gradient becomes incredibly important at A Level Maths. Now, you may have already seen differentiation before. You may have seen this notation, dy by dx. You may have seen the notation f dash of x. They're basically the same thing. These two things equal each other, and they basically stand for the differentiation of a curve. And by differentiation, I basically mean the gradient of the function, and we call this the gradient function. The gradient function then allows me to find the gradient of a curve at any point on the curve. So just bear all that in mind, because it becomes quite important. Little starter, find the gradient of the line joining these points. Okay, look, first of all, if I was doing this at GCSE, and this is just GCSE maths, I would draw a picture. So there's my picture. There's 1, 1, there's 3, 7. You find basically the difference it goes across. And you can just use the x coordinates to do that. 3 take away 1 is 2. And then you do 7 take away 1, which is 6. And you end up with these two values. Now, you may recall what you do to find this. There is a formula which we've seen in A Level Maths. y2 minus y1, x2 minus x1. And if you do that, you get 6 divided by 2. Notice the y's. Now, if that's my quick reminder of how to find the gradient of a line joining 2 points, there it is. Notice I now want to go on a bit from this. So imagine we've got some formula, and I'm suggesting this formula is y equals f of x. Now, y equals f of x lets me put numbers in. So if, for instance, when x is 2, I can find y by going, well, let's put 2 into my function. For instance, if it was y equals an x cubed graph plus 1, then at x is 2, this would give me y equals 2 cubed plus 1. Which is obviously 9. If I pick a different point, x is 6. That's the same thing as saying y equals f of 6. Or if you prefer, y equals 6 cubed plus 1. Well, if you do that, you know your 6 cubes, you'll know that's equal to 217 when you add the 1. Now, look, I've basically got a function y equals f of x, and I want to do it for 2 points on my curve. I don't know what the points are, but what I do know is that I've got one point which is at some magical point x. So if I want to know what its y value is, it's just y equals f of x, because that's what this does. You know, if I put x in, it's y equals f of x. But if I go slightly further over, I'm going to say this x coordinate is x plus h, because I'm saying to you I'm going to go h over. The width of my base of my triangle is h. So this is now x plus h, which means when I sub it in like I've done over here, if I sub x plus h into there, I get f of x plus h. Now, the gradient of my line I want to find. So I suppose what I would do is I'd say, how far up does it go? Well, it's this height, take away this height. If you like my y2, take away my y1, and y2 take away y1 in this case is going to be, well, it's not very nice actually, it's f of x plus h, this one, minus this one, minus f of x. But of course that's not the end of this gradient, because I've got to divide by x2 minus x1. This is slightly better actually, because I've got to do x plus h minus the x, but by definition they're h apart, so if you do that, you will get h. And this is my gradient of my line. This is what I wanted us to find an expression for the gradient of the chord PQ. It may not look very nice, but that is the gradient of the chord PQ. And that's the posh version, if you like. Bear that in mind, because you'll recognize this here. This repeats itself in what we end up using as the differentiation from first principles, but weirdly it's got this additional bit at the front. So the gradient of this function has got this, what we call a limit. A limit as h tends to 0. That's how you'd say what I've just written down here, the limit as h tends to 0. And the idea of this is, if I want to find the gradient of this line here, which I'm calling PQ, well, PQ1 I'm saying, you can see as an estimate of the gradient of my curve does this. And the actual way you do it in science, of course, you should remember this in science, you draw yourself a tangent to the point. When you've drawn that tangent, you find the gradient of this tangent, and you say, well, that's as good as I can get. I can't do it exactly, but it's close to whatever you calculate. Now, I'm trying to find a better method than that, but my first guess, look at this, PQ. If I found the gradient of this line, it's really quite steep, whereas the gradient of my tangent really isn't that steep at all. So actually, my gradient of PQ, if I found PQ1, as it's called here, it's not very good as an estimate of my gradient. But my proper gradient, my gradient of my function, gradient of the function. But notice what I'm thinking of is, well, what if I pick Q2 instead? Well, you'd probably say, well, you could find the gradient of this one, but it's not much better. It's still too steep. But what if I pick Q3? It's getting better. What if I pick Q5? What if I pick Q6? Ah, look how close Q6 is. And if I found this one, if I found one here, and we call that one Q7, it's starting to get really accurate as an estimate of my tangent. And this is what this is about. It's basically saying, if the gap between P and my point, wherever it is, say here, I'm starting off, if this gap is small, which we're calling H, my gap across, if that gap is small, then my tangent, the gradient of my tangent, is actually quite close now to my gradient of PQ. The posh way of saying this is, as h gets smaller and smaller and smaller, in fact so close to 0 it's practically 0, the limit as h tends to 0 is not just roughly equal to this answer now, it's exactly equal to. And this was something that Sir Isaac Newton looked at, and a German mathematician called Leibniz looked at. And we are looking now at the result of their work. So let's get on and show you this in action. So example 1, it says for the function y equals x squared. Well, first of all, I'm going to rewrite this as f of x equals x squared. I'm only doing that because this says f dash of x. So we're using function notation. And the equivalent of dy by dx, which I'm going to find, is f of x. But notice what I said at the start. These two are both versions of the same thing. They are both ways of asking for what's the gradient function. So you might even see the words gradient function as well. Anyway, so if I want f dash x, I'm not sure if I put the dash in there, I should have done. If I want f dash x, or dy by dx, we're going to call it, we write this out. It's the limit. You get in the habit of writing this out exactly as it says it, as h tends to 0, of f of x plus h minus f of x over h. The good news is this formula is given to you. Now this is when you go back to your formula and you say, what does my formula say here? Well, it actually says x squared. F of x is x squared. So I write the limit as h tends to 0. Remember, it's x squared. Now I have to put x plus h into my function. So I'm going to write in this big square bracket x plus h. It said squared. Alright, I'll square it then. And then I take away the proper function minus f of x. Well, my proper function is just x squared. And I then divide it all by h. Now, I know it's a bit annoying, but keep writing this limit as h tends to 0. And I've got to multiply out that bracket. Now, you're either good at these or you're not. It's x squared plus 2xh plus h squared. Don't forget to take away x squared. Don't forget to divide by h. Now, the good news is x squared taken away from x squared disappears. I'm going to write this up here before I lose all space. So x squared take away x squared. In fact, I think the answer is going to come up there. I'm going to carry on writing it here. The limit as h tends to 0 then is now, that's gone. I get 2xh plus h squared divided by h. And look at that. I can divide by h into both of them, so I might as well do that. The limit as h tends to 0. And 2xh over h is just 2x. h squared over h is just h. And this is where the bit of trickery comes in from Newton and Leibniz. Their method basically says as h gets smaller and smaller and smaller, we can effectively at some point ignore it. So they just say ignore it, forget it, just pretend now it's 2x, and that is the answer. Okay, there you go. Good job we did leave that space because it did come up there. Look at that, 2x though, that's the important thing. 2x is what they want. Example 2, let's have a look at this. For the function f of x is 2x cubed minus 1, find f dash of x. They want me to find the gradient function. So f dash of x, we write out the formula. So the limit as h tends to 0 of f of x plus h minus f of x all over h. Now, at this point, chuck in the square bracket, go back to the formula. My formula says 2x cubed minus 1. So the limit as h tends to 0, and I have to put x plus h into my formula. So it's not very nice. It becomes 2 lots of x plus h cubed minus 1. Now I have to take away my function as it properly says. So it might be better putting this into a bracket just so you don't lose minuses along the way. 2x cubed minus 1 all divided by h. Now I've got a couple of brackets there which I need to get rid of. Now we need to multiply out this. We've got to do x plus h cubed. Now that's x plus h cubed is the same as x plus h times by x plus h squared. And the good thing is I know what x plus h squared is. So it's x plus h times by x squared plus 2xh plus h squared. Now if you multiply out, you might need to do it yourself to prove it to yourself. You get x cubed plus 3x squared h plus 3xh squared plus h cubed. So bearing that in mind, I can now come back over here. Notice I've got a double of those. There's 2 of those. So I'm going to go through these and double them. I'm going to write 2 next to each one. 2x cubed. Well, the next one's got 3x squared, so I'm going to make it 6x squared h. Next one says 3x8. Yeah, so this would also be 3xh squared plus 2h cubed. Now I've got to take away 1 because it says so. I've got to take away 2x cubed. And just be a bit careful, minus and minus makes a plus. And all that has got to be divided by h. So equals, the trickery has to carry on, the limit as h tends to 0. Now, things will cancel here, they always do. 2x cubed, take away 2x cubed, that's gone. Take away 1 plus a 1, that's gone. Those don't go. So this is 6x squared h plus 6xh squared plus 2h cubed divided by h. And when you divide by h, of course, you lose a few h's along the way. So what do we get? We get that disappears, so that's 6x squared. This one retains an h, 6x h, and this retains 2 of them, so 2h squared. Now, this is where we use our trickery, as h tends to 0. So that basically means pretend it is 0. Well, that hasn't got anything, but this, if I times something by 0, I get 0, so that goes. 2h squared, let's do 0 squared, that goes. So actually, this is just equal to 6x squared. This is the formula I wanted. So, it may seem weird, but we need to get our heads around the fact that this process, finding the f dash of x or dy by dx, depending on what it's called, from first principles, is an important skill. I dug out a question. This came from an old exam question. We're not going to do it now. I might save it till next lesson. Notice this time it says x to the 4. The exam asks you to do this. Differentiate x to the 4 from first principles. And it's this phrase that tells you that you've got to use this formula. The good news is the formula itself is in the formula book. This is in the formula book that you get given on the day of the exam. But for now, I'm going to save that for the lesson. In a lesson, we'll do more questions from page 253 in the textbook. And it's tricky, but it's definitely something we can do. So all the best.